Hi everyone! Today let's talk about session 4.7, L'Hopital's rule. Big idea! Linear approximations of functions can be used for calculating limits of rational functions near undefined points. Okay, so let's look at this example. Limits of sine x over x. Well, do you remember when we try to find these limits, we plug in 0. Well, when we try to plug in 0, we get sine of 0 is 0. So we have 0 over 0. What does that mean? This doesn't make any sense, right? We know there's a bad guy. Okay, so 0 over 0 because we don't know what it is. The answer could be 0, it could be a number, it could be infinity. Okay, so we call this indeterminate form. So actually we have more indeterminate forms. So let me summarize with you. Okay, so what are the forms we can determine? Okay, so here we can determine. Okay, so we know 1 over infinity, we know that is 0, right? 1 over minus infinity, that's also 0. 1 over 0 plus is plus infinity. 1 over 0 minus is minus infinity. Infinity plus infinity, still infinity. Infinity times infinity, still infinity, right? When you have infinity times negative infinity will be negative infinity. Okay, so for all of these, we can determine. Do we have more? Yes, we can have like e to the infinity, we have infinity, and e to the minus infinity, that is 0 because our exponential function looks like that, right? Okay, so what are the forms we can determine? So here are the indeterminate form. Okay, so we know 0 over 0 we cannot determine. Infinity over infinity we cannot determine. And 0 times infinity we cannot determine. Infinity minus infinity we cannot determine. Okay, and there are more. 1 to the infinity we can determine. Infinity to the 0 we cannot determine. 0 to the 0 we cannot determine. Okay, so today we're going to go over those indeterminate form. What do we do? And if you can remember the limits of sine x over x, well, this is in session 3.4, and we use the proof of geometry of the unit circle and the triangles. We show this is 1. Okay, and today let's look at the linear approximation for sine x. So last class, session 4.5, when we talk about the linear approximation, we calculate the linear approximation for sine x is x. Okay, if you can remember, that is example 2 of session 4.5. Okay, and here you can see the denominator g of x is its own linear approximation, so we can use the linear approximation of sine x over the linear approximation of x, which is x itself. So if we approximate it by the linear approximation, you can see x over x is, they cancel, and then we get 1 over 1, which is 1. Okay, so even though we use a linear approximation to evaluate the limits, and it seems like this should be okay because the linear approximation approximates the functions better and better as x get close to 0. Okay, and you can see our answer agree with what we have in session 3.4, right? So in more general case, suppose that we have the limit f of x when x goes to c equal to 0, and we have the limits of g when x goes to c is also 0, so that we have like a 0 over 0, okay, this case. And then in this case, let's use the linear approximation to calculated. So we replace f of x by the linear approximation as c. We replace g of x by the linear approximation of g as c, okay? And furthermore, because the limit of f of x when x goes to c equal to 0, that means our f of c is 0. And our g of c is 0, so we have 0 and 0 there, right? So that means we can ignore those terms. We only get like f prime of c, x times x minus c on the top, and we get g prime of c, x minus c at the bottom. Now, do you see the bad guy? Yes, the bad guy is x minus c. It makes the numerator and denominator 0. After we cancel the bad guy, our answer is f prime of c over g prime of c. Okay? Yeah, and L'Hopital's rule asserts that this really works. Okay, this does work. So this is the theorem of L'Hopital's rule. Suppose f and g are differentiable, and we also suppose the derivative of g is not 0 near a, except possibly at a. Suppose that the limit of f is 0 when x goes to a, and the limit of g is also 0 when x goes to a. Or we can also suppose that the limit of f goes to plus or minus infinity, or the limit of g goes to plus or minus infinity. In other words, we either have an indeterminate form of 0 over 0, or we have infinity over infinity. Then the L'Hopital's rule tells us that the limit of f over g equals to the limits of f prime over g prime if the limits on the right-hand side exist, or the right-hand side, the limit is infinity or minus infinity. Okay, so here are a couple remarks. Okay, so remark 1. Remember here, we have f prime over g prime. So we are not doing quotient rule. Sometimes students say, oh, limits of f over g, use L'Hopital's rule. Then it's like f prime g minus f g prime over g squared. No, we're not doing quotient rule. We are not doing quotient rule. We just use the derivative of f over the derivative of g. We're not doing quotient rule. This is the quotient of the derivatives, okay, but not quotient rule. That is the first remark. The second remark, okay, so the right-hand side, we can use L'Hopital's rule if the right-hand side exists equals to a number, or it could be infinity or minus infinity. Why can we allow this happen? Well, think about it. Think about it. If the limit x goes to a of f prime over g prime is plus or minus infinity, that means the limit x goes to a at g prime over f prime is gonna be, see, what's the difference? We flip them, right? So we flip them. This is like 1 over plus or minus infinity. That is 0. So 0 exists. Okay? So instead of working on f over g, you can use like the L'Hopital's rule of like g of x over f of x equals to, so by the L'Hopital's rule, that is, x goes to a and g prime of x over f prime of x, and we know that is 0, okay, because this guy exists. So that's why we know the limit of f of x over g of x, which is the limit 1 over g of x over f of x. So we know it's plus or minus infinity. Okay, so L'Hopital's rule also holds if the right-hand side limit equals to infinity or minus infinity. Okay, so you might ask, okay, well, it holds when the right-hand side is a number, and it could be infinity, it could be minus infinity. So that's like all the possibilities. So when will the L'Hopital's rule doesn't hold? Okay, so the L'Hopital's rule doesn't hold. Okay, even though you satisfy the hypothesis 0 over 0 or infinity over infinity, the L'Hopital's rule doesn't hold if the right hand side, the limit of the right hand side, which is like the limit f prime g prime, this guy, the limit does not exist. Okay, this does not exist means we cannot use infinity or minus infinity to describe. It's like oscillating between two numbers. Because even though it does not exist, if it's infinity or minus infinity, we can still use L'Hopital's rule. But if the limit is like oscillating between two numbers, like 1 or minus 1, in this case, we cannot use infinity or minus infinity to describe it. So in this case, L'Hopital's rule doesn't hold. Okay, so those are the 3 remarks. Let's work on our example. Okay, so example 1. So this is our example 1. Okay, so the first steps, when you plug in -2, what do you get? X plus 2 is 0, right? And x plus 3 is 1, but ln of 1 is also 0. So we get 0 over 0. Oh, we can use L'Hopital's rule. So at the steps you are using L'Hopital's rule, please make sure you are checking the conditions, hypothesis. Okay, we should have like either the case 0 over 0 or infinity over infinity. Okay, and also tell me you're using L'Hopital's rule. Okay? Then that is the limit of the numerator prime and the denominator prime. Okay, so what is that? So the numerator prime, derivative of x is 1. Derivative of 2 is 0. How about the denominator? Well, the denominator we are using chain rule. This is u. So the derivative of ln of u is 1 over u times u prime. But u prime, which is x plus 3 prime, is 1. Oh, so this is the same as, we can flip it back. Remember, we're using the formula of a over b over c over d equals a over b times d over c. So that is why the x plus 3 is actually like the d, so it's in the numerator. Okay, and we plug in x is minus 2. Minus 2 plus 3 is 1. So 1 is our answer for this problem. Okay, everybody? That is example 1. Let's continue to look at example 2. Okay, so when x goes to infinity, so when you are evaluating the limits, you have to look carefully where is the x approaching. Okay, is it approaching a point, a number, or is it approaching infinity or minus infinity? Okay, so in this problem, we have x approaching infinity. So when we try to plug in infinity, what's 3 to the infinity when x goes to infinity? Well, this is exponential function because the base is 3. 3 is greater than 1, so the exponential is actually increasing. So we see it goes to infinity. How about the denominator? Well, the denominator is a polynomial. It also goes to infinity. Well, infinity over infinity, we can use L'Hopital's rule. Okay, so we use L'Hopital's rule. It means we take the derivative of the top guy over the derivative of the bottom guy, what do we get? Derivative of 3 to the x, do you remember what is that? What is the formula for it? Well, b to the x prime is, father looks like the son, but the father has a fancy mustache, right? ln of b in this case. So, we have 3 to the x, ln of 3. And the derivative of x squared is 2x. The derivative of x is 1. Okay, so this is what we get. Well, what happened when we let x goes to infinity? The numerator, we still have the exponential function. So that's infinity, the bottom, 2x plus 1, a line still goes to infinity. So what do we get? We use L'Hopital's rule one more time. So it might happen that we need to use L'Hopital's rule a couple times. Okay? Well, then we have the numerator prime times over the denominator prime. Here we're not doing quotient rule, so don't do quotient rule. Actually, quotient rule is even harder right here. Here we're just doing quotients of derivatives. Okay. So ln of 3 is a constant multiple, stay here. And then 3 to the x, we have an extra ln of 3, right? And the derivative of 2x is 2. Derivative of 1 is 0. Okay, now what happened? Well, we simplify it. This is the same as ln of 3. We have 2 copy of that. Okay, and then times 3 to the x over 2. Okay, now you see, when x goes to infinity, 3 to the x goes to infinity, but the denominator is a fixed number. So numerator goes to infinity, but denominator is a constant. The answer is infinity. So the answer is infinity. We can still use L'Hopital's rule. L'Hopital's rule holds here. Okay, so what can we summarize? Can you see for exponential function? For exponential function, when you take the derivative, what happened? Well, the exponential function just stays all the way along, right? But how about the polynomial? The polynomial, when you take the derivative, the degree of the polynomial actually decreases by 1 in each step. So we start with x squared, but now we get 2x, and then we get a constant term. So you can see the exponential function stay the same, right? Stay there, but the polynomial is actually dropping down the degree. So eventually, the polynomial it becomes like a number. Okay, so that's why the exponential function grows faster than all polynomial. Okay, here you can see we have numerator. So we have numerator is exponential function. The denominator is polynomial. Oh, sorry. I mean, let's put in general denominator. Okay. So when x goes to infinity, if the numerator over the denominator is infinity, what can you say? We know that the numerator grows faster. Okay, so if the numerator over the denominator goes to 0, what does that mean? It means the denominator grows faster. Does that make sense? Your numerator and denominator, your denominator bigger. So your number is smaller. The denominator grows faster. Okay? Alright, so that's why here our answer is infinity. We know the numerator grows faster, so the exponential function grows faster. Okay? So that is example 2. Let's continue to look at example 3. So example 3, we have the limit x goes to infinity of ln of x over square root of x. And you can see here, when x goes to infinity, we have the ln of x goes to infinity, right? So this is natural log of x. How about the square root? Or the square root like that. It also goes to infinity. Okay, so we can use L'Hopital's rule. So that's the derivative of the top over the derivative of the bottom, but let's write it as the standard form. So x to the 1/2. Okay, so let's differentiate it. The derivative of the top guy is 1 over x, right? The derivative of the bottom guy is 1/2. X to the minus 1/2. Okay, what does that mean? Well, that means, so the top we still have 1 over x, but the bottom we have 2. X to the negative, it means is actually in the denominator, right? And because it's square, 1/2 means square root. Okay, so let's flip them and simplify them. So 1 over x, 1 stay on top, x bottom, 1 here, so 1 also stay at the bottom, and then 2 and square root of x will actually goes to the top. Can you simplify? Yes. How? So you can see x is actually square root of x times square root of x. So you can cancel one of the square root of x. Then we will get a limit. X goes to infinity of 2 over square root of x. So numerator is constant, denominator going to infinity. So the answer is 0. Okay. So what's the numerator? We start with, so the numerator is logarithm function, and the denominator, this is not polynomial, but it's a power function. Okay, and when the limit is 0 when x goes to infinity, that means the numerator is bigger or the denominator is bigger. So it means the denominator, okay, is bigger or grow faster. Okay, grows faster. So i.e. the power function, so square root of x is the power function. So power function grows faster than the logarithm function. Okay, so that's why we have second, the logarithm function grows slower than other polynomial. So actually not only polynomial, okay, but also any power function. Okay, it can be square roots, it could be like to the 5/2, any power function. Okay, like x to the p, any p. Okay, so that is example 2 and example 3. Okay, so if we want to draw a growth rate sequence, a growth rate sequence would be like we have the ln of x that grows slower than x of p, and who's the fastest? Exponential function. So this is like the growth rate sequence. Okay, so growth rate. Okay, then let's continue to look at example 4. Okay, so first of all, we have x goes to 0. So let's plug in 0. So when we plug in 0, we have limits. X goes to 0. So 5 times 0 is 0, tangent of 0 is 0, and the denominator is also 0. So we have 0 over 0. Wow, we can use L'Hopital's rule. So far, so good, everybody? So we can use L'Hopital's rule. So that's the numerator prime. over denominator prime. Let's continue and differentiate it. Okay, so what is the derivative of 5x? The derivative of 5x is 5. The derivative of tangent is secant squared. But because of chain rule, we have an extra 5. 5x prime is 5. And then the bottom derivative of x cubed is 3x squared. Okay, so I strongly suggest that you can pause the video and work on the problem first, and then we can check our answer together. Okay, what do we have now? Well, the numerator, we have 5 minus secant squared 5x, right? And the denominator, we have 3x squared. Okay? So, let's see. When we plug in 0, what's secant 0? Well, secant is 1 over cosine, right? So 1 over cosine is what? 1 over cosine is, when we plug in x is 0, is 1 over cosine of 0 is 1. So it's still 1. Secant of 0 is 1. So the numerator, we still get 0. The denominator, we still get 0. Okay, so actually from this step, we have 2 ways to continue and solve the problem. Let me show you both ways, then actually you can compare and choose the way you like. So here from there, so we have a method 1. Continue to use the L'Hopital's rule. So we have 0 over 0. So use L'Hopital's rule again. 5 minus secant squared 5x times 5 over 3x squared prime. So the derivative of 5 is 5, and minus 5 stayed here. Derivative of secant squared, well, the secant squared is like chain rule, right? It's like u squared, so it's 2u and u prime. The bottom, we have 6x, okay? So let's simplify it. U prime, what's the derivative of secant? Derivative of secant is secant tangent. Okay, so minus 10 secant 5x. Derivative of secant 5x is secant tangent. And there's extra factor of 5. Alright, so what is that? Well, that is negative 50, and then times secant 5x squared times tangent 5x, right? All over 6x. So far so good, everybody? Okay, so when you plug in 0, oops, sorry, I forgot my limits. So don't forget your limits. We have to carry all the steps. Okay, so you can see when you plug in 0, we just get 0 over 0. So we should use L'Hopital's rule again. Even though you can see the numerator is more complicated, but it's okay. Our denominator is getting more and more easier, right? Actually, the next step when you differentiate, you should get 6. 6 is a constant term, so hopefully we can stop at the next step. Okay? So denominator 6x prime is 6. The numerator, we're gonna do product rule. Okay, so product rule. First of all, the minus 50 we can put it outside, right? Minus 50, and then times, we can put it outside. Then we don't need to worry about that. Okay, so it's this guy times this guy. So it's the derivative of the first guy times second guy plus first guy, the derivative of the second guy. The derivative of tangent is secant squared times 5, right? So far, so good, everybody. Okay, and what's the derivative of secant squared? Well, you gotta use chain rule, and then derivative of secant squared is 2 secant 2u times u prime. But actually here, you don't need to calculate it because of this tangent. You see, when you plug in x is 0, tangent of 0 is 0, this is gone. So that's why we have negative 50 over 6, and then the first term is 0, the second term, secant of 0 is 1, so it's 5. So we have negative 250 over 6. 2 is a common factor, so we have negative 125 over 3. So this is our answer. Okay, we just keep using L'Hopital's rule. Alright, let me teach you another method. Okay, so method 2. Okay, so starting from there, let's continue. Okay, can you see the numerator? We can factor out the 5. Then we have 1 minus secant squared. Okay, so what's 1 minus secant squared? Well, if you're familiar with the trig identities, secant squared minus 1 is tangent squared. So 1 minus secant squared is negative tangent squared. So this is negative 5 tangent squared. Alright, so this is like trig limits. Do you remember trig limits? Well, we changed the tangent in terms of sine, cosine. So this is like sine squared over cosine squared. And then we have 3x squared down there. Okay, what do we do next? We want to split. See, all the concepts are actually connected. So split sine 5x, sine 5x, and we have cosine 5x, cosine 5x. How about 3x squared? Well, okay, I can put the 3 here. I can put x squared. I can split them. X here, x here. Okay, why do I want to do that? Because remember, you want to match sine u over u. That's 1. So this is 5x. You know you're going to match 5x here as well. But you already have an x, so you can put the x here. So you don't need to match a 5x. You just need to match a 5. It's like you want to have $10, but you only have $5. You can borrow $5 from the bank. You don't need to borrow $10 from the bank, right? Because you already have $5. So let's start to match. So here we want to match a 5. When you divide it by 5, you also need to multiply by 5. Here you match with 5. When you divide it by 5, you also multiply by 5. For cosine, what do you want to match? So cosine 0 is 1. 1 is okay in the denominator, so we don't need to match anything. So just put 1 there. Okay, and then just put 1 there. Okay, what do we get at the end? Negative 5 third. And then next one, sine 5x over 5x is 1. Sine 5x over 5x is 1. 1 over cosine 5x is 1. 1 over cosine 5x is 1. And this is 25. Okay, so that's negative 125 over 3. You can see they are the same. And first method, what do we use in the first method? The first method we use L'Hopital's rule. Okay, so the first method we use L'Hopital's rule. How about the second method? Well, the second method we use the trig identity and the trig limit, which is in section 3.4. Okay, everybody? Let's continue. Okay, so this is example 5. We want to find the limits of x goes to infinity of sine x plus sine x and over x plus cosine x. Okay, let's see what happened. So when x goes to infinity, what happened to the numerator? Well, the x goes to infinity, right? So here we see the numerator goes to infinity, and the denominator also goes to infinity, right? Wow, infinity over infinity. Wow, we can use L'Hopital's rule. Let's use L'Hopital's rule and see what happens. So we take the numerator prime over the denominator prime. Okay, what happened? Derivative of x is 1. Derivative of sine is, what is that? Do you remember? That's cosine x. Derivative of x is 1. Derivative of cosine is negative sine x. Okay, now what happened? Oh, can you see sine and cosine? They are both oscillating between 1 and minus 1. So what happened? Well, the numerator and denominator, they're both oscillating between 0 and 2. Okay, so here, numerator and the denominator oscillate between 0 and 2. So the limit does not exist. So this is the case. Do you remember in the last page when I introduced the L'Hopital's rules? I said the L'Hopital's rule holds if the hypothesis is like you see 0 over 0, infinity over infinity, and the limit on the right hand side, like f prime over g prime, you get a finite number, or you can get infinity or minus infinity. So in those cases, you can use L'Hopital's rule. But there's one special case you cannot. It's when there are limits of the right-hand side. Okay, the f prime over g prime, the limit does not exist. So this is an example. We cannot use L'Hopital's rule. Okay, so it doesn't mean that the limits. So sometimes students get confusion here. Okay, so in this problem, the limits of f prime over g prime does not exist. So we cannot use L'Hopital's rule here. Okay, it doesn't mean the limit of f over g does not exist. It might exist. Okay, we just don't know. Okay, we just cannot tell from the L'Hopital's rule. So that's why, what is the correct solution for this problem? Okay, yeah, you're right. What we just said, they're wrong solution. So, because I want to show you sometimes, it take more effort to the correct solution. Okay, so those are the wrong solution. L'Hopital's rule cannot use it. So this is the correct solution. Okay, well, let's look at the numerator and the denominator. Okay, what's the dominant term of the numerator? X and sine x, which one dominates as x goes to infinity? Of course, x, right? Because sine x just oscillating between minus 1 and 1, but x goes to infinity. So the dominant term is x. How about the dominant term of denominator? Well, that's also x. So this guy is actually x over x. That is 1. Okay, so this is like our shorthand proof. So, okay, what is the formal proof? Well, the formal proof is actually, okay, so this is the formal proof. Okay, we can use the shorthand proof. Okay. I taught you shorthand proof and the formal proof. So the formal proof is actually we have numerator and denominator. We both divided by x. Okay, so we can do that. We can divide the numerator and denominator both by x. Now, let's distribute it. So x over x is 1, and sine x over x is, and the denominator we have 1 over cosine x over x. Okay, so when x goes to infinity, what happened? Well, the limits x goes to infinity of sine x over x is actually 0 by squeeze theorem. We showed that before because sine x is bounded between minus 1 and 1. So sine x over x is bounded between 1 over x and minus 1 over x. So when x goes to infinity, those two boundaries goes to 0. So the middle guy has the same limits. So that's the squeeze theorem. So similarly, cosine x over x is also 0 by squeeze theorem. So that's why we have 1 plus 0 over 1 plus 0. The answer is 1. See, we have the same answer. And that's the formal proof. So far, so good, everybody? Yes, so this is an example that we cannot apply L'Hopital's rule. But we can use other method to solve the problem. Yes. Okay, so example 6. We want to find the limits of x goes to pi over 2 from the left, of 1 plus tangent x over secant x. Okay, let's solve it. First, let's plug in pi over 2 from the left. So you know what's tangent? What's the picture of tangent? Oops. So this is a picture of tangent x. So when x goes to pi over 2 from the left, you can see tangent goes to infinity. And how about secant? Well, secant, you look at the graph of cosine, right? Secant is 1 over cosine, so that's why this is, let me use a different color. Oops. Oh, sorry. Let me come back. Sometimes I touch the screen using my fingers and then Alright, so that was cosine, and secant is 1 over cosine. So the picture looks like that. Okay, when it's about to set pi over 2 from the left, you can see it also goes to infinity. So infinity over infinity, we can use L'Hopital's rule, right? So that is limit x goes to pi over 2. Okay, and the derivative of the numerator over the derivative of the denominator. And let's continue. The derivative of the numerator, the derivative of 1 is 0. And the derivative of tangent is, do you remember what that is? Secant squared. And what's the derivative of secant? Secant tangent. So far, so good, everybody? Okay, can you see? We can simplify. So when you do the L'Hopital's rule, when you see a quotient that you're able to simplify, please, you gotta simplify it. Because you don't want to take the derivative of this guy. It requires chain rule. You don't want to take the derivative of that because it requires product rule. So after you simplify it, we only get secant over tangent. Okay, so when we plug in pi over 2 from the left, Oh, we also get infinity over infinity. So we use L'Hopital's rule. What happened? So we get secant derivative is secant tangent. And derivative tangent is secant square. Oh, does that look familiar? We can simplify the secant, and what do we get? We get tangent over secant. We take tangent over secant. Wow, it looks like this. So actually, this is still infinity over infinity. If you use L'Hopital's rule again, you will get this guy back. So this is like a recurrence situation. So sometimes L'Hopital's rule doesn't work because you get to like a circulating situation. When you keep taking the derivative, you just get those terms back and forth. So in this ways, L'Hopital's rule doesn't work, and you gotta use another method. Okay, so always try, if you see a trig functions, always try the trig identities. Okay, so here, so starting from this guy. Okay, so from this guy, let's continue here. So starting from here, we use the trig identities. So because we're more familiar with sine and cosine, so I suggest you change everything in terms of sine and cosine. So secant is 1 over cosine. Tangent is sine over cosine. What happened? Cosine cancel. So we have 1 over sine x. What is sine? Sine of pi over 2 is 1. So the answer is 1. Okay, so when you work with trig functions, think about more of the trig identities. So you can see the previous examples, when there are 2 ways to solve the problem, I show you 2 ways. So I want to ask you to keep your mind open, keep trying different methods. Sometimes one works, sometimes one doesn't work. So try the other one, okay? So when you have questions, feel free to print screen and ask me. Cheers! Okay, so what we just did. So we talk about the indeterminate form of 0 over 0 or infinity over infinity. So now let's continue to go down the list. Okay, so let's look at the indeterminate forms of infinity minus infinity. So the trick is combine the difference into one expression. How? Okay, let's look at example 7. So combine the difference into one expression. So, well, what is x? Can you see there is a ln here? So that reminds me the ln property. The ln property is ln of a times b is ln of a plus ln of b. ln of a over b is ln of a minus ln of b. So here I want to rewrite the x as ln of something. Well, that's ln of e to the x, right? Okay, see, now both of the terms contain the ln. We can actually combine them. So we're using this formula. So we have e to the x over x. Okay, do you remember exponential function and the polynomial, which one grows faster? That is the exponential function, right? So that's why the inside the inside will goes to infinity because the exponential function grows faster than the polynomial. Or you can use L'Hopital's rule, or you can use L'Hopital's rule to show that. And actually how we conclude the exponential function grow faster than the polynomial is using the L'Hopital's rule. Okay, we take the derivative is still e to the x, the bottom become 1, so that's why it's infinity. And then ln of infinity, so ln of x when x goes to, ln is like that. So when x goes to infinity, ln of x also goes to infinity. So the answer is infinity in this case. So far so good, everybody? Yes. Next. So when x goes to 1, you can see ln of 1 goes to 0. So 1 over 0 is infinity, right? The other one, 1 over 0, is also infinity. So in this case, infinity minus infinity, we want to combine them and get a single expression. So this is different fractions. So let's combine the fractions. So we have the common denominator is ln of x and x minus 1. And then we have the first term multiplied by x minus 1 on the numerator and denominator. The second term multiplied by ln of x from the numerator and denominator. Okay, so this is how we combine them. Let's see, when we plug in 1, the numerator we get 0 minus 0, so 0. The denominator we get 0 times 0, so 0 over 0. Yay, L'Hopital's rule. So that is the numerator prime over the denominator prime. Alright, so let's calculate what that is. Derivative of x is 1. Derivative of 1 is 0. Derivative of ln of x is 1 over x. And the bottom we have product rule. So it's ln of x prime times second guy plus first guy times second guy prime. Okay, what do we have? Derivative of ln of x is 1 over x. And then derivative of x is 1. Derivative of minus 1 is 0. So this is what we get. Always keep in mind, we don't like fraction in a fraction. So if you see a fraction, get rid of the fractions. So multiply the numerator and denominator by x. So that will help us to get rid of the fraction. So distribute x times 1 is x. X over x is 1. X times this guy, 1 over x cancel. We have x minus 1 plus x times ln of x. Okay, so let's see, when we plug in 1, we get 0 in the numerator and we also get 0 in the denominator. So let's use L'Hopital's rule again. And actually you can see when we use L'Hopital's rule again, the derivative of the numerator is actually 1, right? So we know, okay, one more time of the L'Hopital's rule, we'll get our answer. So continue, don't give up, just continue. Okay. Yeah, sometimes you are on a problem, you see, oh, it's so complicated, it's long. Do I did something wrong? Oh, but you can see here, after this step, the derivative of the numerator would be 1. We love to see 1 because if you keep getting 0 over 0 or infinity over infinity, well, then you have to keep using L'Hopital's rule. But now, see, the numerator's 1 is actually help us to like say the steps. Hopefully, we can stop this process. And the derivative of the denominator, derivative of x is 1. And then derivative of minus 1 is 0. And then we have a product. So product rule, first guy prime, second guy, plus first guy times second guy prime. So first guy prime is derivative of x is 1. So ln of x plus x. Derivative of ln of x is 1 over x. So they cancel. We get 1 here. So sometimes students say, oh, they cancel, we get 0. No, here we cancel, but we get 1. Alright, so we get limit x goes to 1, 1 over 2 plus ln of x. Yay, when we plug in x is 1, we get ln of 1 is 0, so we get 1 over 2 as our answer. Okay, so that is example 8. Okay, let's continue. So example 9, we want to find the limits of, so this is a difference between 2 terms, right? But can you see this is like difference of square roots? So when x goes to infinity, we still have infinity minus infinity. But this is like a difference between square roots. When you see difference of square roots, what do you do? What do you do? Some words start with a C. Yes, conjugates. So multiply by the conjugates in the numerator and denominator. Now what happened? So keep in mind that a square minus b squared is a plus b, a minus b. So then here we have the first guy where we get rid of the square root. Minus x squared. And the denominator stay the same. So don't forget this guy. So we have some students forget about this term in their quiz. So don't forget that. Now x squared cancel. Okay, now let's see what happened. We have 5x plus 2 over square root of x squared plus 5x plus 2 plus 1. So far, so good. So here, oh sorry, that's x. That's not 1. So here, think about it. You can use L'Hopital's rule, but you can see when you take the derivative of this guy, it's quite complicated. So actually here, you do not need L'Hopital's rule. We just need to look at the dominant terms. Okay, so what's the dominant term of the numerator? 5x. What's the dominant term of denominator? Well, what's the degree? This is like square root of x squared. That's like degree 1, but there we have another term with degree 1. So that is absolute value of x plus x, but because x going to infinity, so x is positive, so the absolute value of x is x. So we have 2x in the denominator. That's why this guy behaves like 5x over 2x. When x goes to infinity, the answer is 5 over 2. So the answer is 5 over 2. So you can see this problem, we didn't use L'Hopital's rule. You can also use L'Hopital's rule, okay? But it's just like more complicated. Okay, so we're done with this problem. But I want to show you, what if we use L'Hopital's rule? Okay, so when we use L'Hopital's rule from this set, because we have infinity over infinity, so we can use L'Hopital's rule. So we get the top guy derivative over the bottom guy. Take the derivative. The bottom guy derivative. So the top guy derivative is easy. That is just 5. But the bottom guy, we have the chain rule. So this is like u to the 1/2. So it's 1/2 u to the negative 1/2, right? And then plus derivative of x is 1. Okay. Oh, sorry, we forget u prime. So u prime is actually 2x plus 5. Okay, now what happened? This guy is 5, but the bottom is like 2 square root of x squared plus 5x plus 2. And then this is 2x plus 5, and that's minus x. Okay, so when x goes to infinity, and here we cannot really tell. We cannot really tell what this is. So what do we do is we still need to simplify. So combine this, take the common denominator and simplify this quotient, and then continue. But you can see this guy is actually more complicated than what we start with. So in this problem, using L'Hopital's rule make the problem even more complicated. That's because the square root function, when you differentiate, the derivative is quite complicated. Okay, so for this example, it's better to look at the dominant term of the numerator and the dominant term of the denominator. Okay, and so L'Hopital's rule, I don't suggest to use here. So that's why sometimes you use one method, you get stuck. Don't just keep going. So how about try other methods? Maybe you can find another way which is much easier. Okay, everybody? So let's continue in part B.